Okay, hello everyone. Welcome to another lecture for 165. And so today we're going to focus on disk and files and sort of finish up our conversation from last week. And then we will move to discussing the sort of the key storage architecture design for Outstore. So last week we kind of talked about variable length record size, then we talk about fixed record size. And in the same theme, we also talked about how do we, now that we know what the structure of a single record is, how are we going to place it on pages? So one simple design of page format, which is a fixed length record. And I think this should be actually sufficient for the first milestone, or even for the entire milestones in this course, is that we can think of a page as a set of fixed slots, and in each slot, one entire record fits. And within each page, we're going to have the first end slot kind of filled, and then we're going to have some free space, and then we may have some header information like number of records. So now if I'm adding the new records, I could just add it to a new slot in a page. The challenge with this structure is that in my record ID, in my read, if I'm maintaining the page ID and I'm maintaining the slot ID, so that points to a particular position in this page. Now, if I were to delete this, then I can kind of mark it as deleted, and I would kind of lose this slot forever because I cannot read it. So that slot is kind of dedicated to that particular read. So I can't really use that slot anymore. And one way of reusing that is to reorganize this page and try to reclaim the empty space. But any reorganization of this page, it may result, or it will result in invalidating some of the existing reads for some records, because before they were on the 5th slot, now they're going to be on the 3rd slot. So there is a shifting that is happening. In addition to the cost of maintaining this page, as a result of reshuffling, we may invalidate some of the existing read. Alternative to this design, also pretty straightforward, having a fixed slot size, but instead, what we could do is to kind of, in our header, we keep track of which slot is empty, which slot is full, and that kind of recorded in this bitmap as if it's a 1, if it's taken, if it's 0, you can say it's empty, or the other way around, doesn't really matter. And again, if there is something that is deleted, then I could mark that slot available, and I don't really need to reshuffle things. I could potentially just assign that slot to a new record without the need of reshuffling. And so it's not going to be packed. This one is always going to be packed. So the idea here is that I want to maintain it to be always packed. Here I'm relaxing it. I say I don't need it to be packed. I could have empty space in the middle. Both of these are talking about the record. In our assignment, or in Outstore, or any column store, this slot could be fixed as well, as long as you assume the size of your column is fixed. And I think we're making that simple assumption for this assignment, or for the entire course, that our record is of not only our records of fixed size, but also each column is of fixed size. So each of these pages can be used for one column, to maintaining one column or one attribute of every record. So if my record, I have 4 columns, then I will have 4 of these pages. And the 4th slot on every page will correspond to the 4th record. And just the nature of the way Outstore works, because you only do an append only, you only do an append only to base pages, and you only do an append only to tail pages, this simple design of packed and insertion only is a perfect fit. It's a simple design, easy to implement, and it actually can be utilized because there's never a need to go back and forth. Our updates or insertion are always strictly append only. So it's a perfect fit for the design that we have. Any question?
I have a quick question just about kind of the nomenclature we've been using.
Sure.
After kind of going through the assignment, the milestone assignment a little closer, it looks like that when sometimes we're referring to page, and page is really a set of things instead of one thing. So just for example, it seems to be in that assignment that a base page refers to a set of physical pages. It's not singular, is that right?
That is correct.
Okay.
And the reason for that is because normally when we talk about the row store, we can talk about a single page, and that's independent because the entire record that fits there. But when you talk about the column store, every column is in a different page. So that's where the exact point that you mentioned. So when we talk about base pages, we talk about more in the abstract sense, the pages that are to store the original inserted version of the record. And then the tail pages are the updates. And later in the later milestone, we'll talk about merging the recent tail pages with the older base pages to consolidate, but that's coming up. But for this point is that the base pages is the originally inserted record, and since the single record spans on multiple pages, so the concept of the base page internally is implemented as several pages, one for each column. Tail pages, exactly the same concept. So the concept of the tail pages is for the insertion or the append only of the changes to the record. And again, the tail pages span, let's say if every column is getting updated every time, so the tail pages also span a set of pages, one for each column. And from the low level of the database, they're all just pages, whether it's base page, whether it's tail page, whether it's for the second column, or whether for the first column, every single thing is a base page, can be referenced by a page ID and slot ID. So this abstraction is really come actually at the higher tier. At the lower tier, if you were kind of implement this in a sort of in a commercial database, that's really another important thing, is that the concept of base page or tail pages, they're slightly higher level concept. At the base of it, they're all just pages, and each page has a set of slots. So that's the sort of the base primitive. Page is a basic primitive that is the main element for constructing base pages or tail pages. Again, that's another important question. Any other remarks? Again, as kind of have said that my goal is to make these as interactive, as engaging, and if we end up covering less material in the course, it's not a really concern. I think what's more important is that we really get a good understanding and and then we can go ahead and put it into use, what we're learning. And that's something that we're going to remember 3 months, 4 months, 5 months, or hopefully a few years from now, as opposed to kind of just sifting through different topics. Well, there's a good chance we're not gonna retain any of it soon after the course ends, or even maybe after the lesson ends. So again, I want to take my time and really make sure everybody understands it and everybody's on the same page. Okay, so this is a different page layout design, and it's kind of the standard design. So any commercial database that you take, they have actually some variation of this design. It's a very flexible, and it does really accommodate sort of the key needs. And that key needs is that if I put something onto this page and later, and this is especially is a variable length, and later I need to update it or add something to it, then I may be forced to reorganize this page, move around other records, or at least move this record around. So now, if in my read I have page ID and I have slot ID, and the slot ID you can think of it as the offset of where the record starts. If I put the actual offset, the physical absolute offset of the record into the read, then for any movement of bits in this page, that offset may change. That means any internal restructuring of a page will change my read, my stable read, or I won't be able to have a stable read. So this basic idea, I introduced indirection, and this idea of indirection, we will see it developed over and over and over again throughout the entire course. So the simple idea of the indirection is that the read points to a page ID and a slot ID. And within the slot ID, I can write the physical offset. So if today the physical offset of a record is 24, and tomorrow the physical offset of the record is 176, doesn't really matter. The read doesn't change. So any changes done in this page is abstracted out from that, from the notion of the read. And the notion of the read is something that is used in indexes and everywhere else. So if our read constantly get changing, I actually not only have to potentially invalidate a bunch of other reads that are on that page, but I also have to go change all the indexes because the indexes were pointing to read. So this design of adding this slot directory or add this indirection will fix the changes to the read. And again, this indirection is so important, basic, very simple concept, very important. And we see it's going to really see its development throughout the course. I mean, put another word, I spent 4 years of my research career working on indirection. Sort of just the simple idea of indirection. And so it is simple concept and yet very powerful. There's so much interesting thing that one can be use it for. Lots of creative ideas can be unfolded from it.
I have a question. So yes. the read will always have the same page ID, but it points to a value which is offset by the slot directory. So
so the read points to a page ID and a slot number here, and the slot number is fixed. The page ID fixed, slot number fixed. But if and in this slot space, it points to the physical offset. So even if my record gets moved around, it's just this offset, the value of the offset changes. But this particular slot is always dedicated to that read. So the read never changes. But in order to figure out where is the actual record is on the page, now I need to consult this directory, essentially go to a level of indirection before I can find the original offset. In the previous examples, this slot ID was the actual offset. So there was no need of having to do that indirection, that additional lookup. I could just go directly to this spot in that page. But then we face those problems that I mentioned.
Okay, and my last question on this would be, because it appears that it's like two-dimensional, but the offset is just a number. Like, I guess that's not clear to me.
Two-dimensional in what sense?
Well, like we could see that the first one where the read, where it has n, it's higher up than the other ones. So
these ones?
Yeah. Like when I think of offset, I think of like one axis, but it appears that it's two, at least in this picture.
So the I is the page number. So these are all this is page I. So that's why the first value is I. So this is page I. So every record, any read in this page will have page I. The only thing that would change is a slot number. for every record. This record is a slot number 1. This record is slot number 2. This record is slot number n. Okay? But now you're saying, well, why is it the slot number 1 is after slot number n? That's the question that I guess you have.
Well, I'm imagining if they're variable, like their variable length, then it wouldn't be so neat as just stacking them in like one axis. So I'm assuming that.
So there's no axis here. This is just a free space. So initially,
Okay.
it might have been the case that this is the first inserted record initially was on the top, and then the movement happened at some point, although that it's the first element that was inserted after page got reshuffled and moved around, it's somewhere else in the page. And that's okay, because as long as we know this is the rid of page I, slot I, it could be anywhere on the page, and all I need to know is to come to this slot number 1, and from here I get an offset of where actually physically that record is. So it doesn't really matter where it is. As long as I know I have a fixed page ID and I have a fixed slot ID, I can go to that slot ID and figure out exactly where in the page currently that record resides. And maybe the next time I read it, this might have been moved to somewhere else on the page, and that's okay. My read doesn't change. And that's the key element here.
Okay, that makes sense. Thank you.
You're welcome. So now, so we talked about how do you structure a record. We talked about how do you put records or columns into page. And so one other thing is, I think we can kind of, and then we could have simple file structure. We talked about this already. Pages could just be just unordered files or just pages. It doesn't really have to have any specific thing. But one thing I think becomes interesting, I'm going to skip some of these because I think we've kind of talked about it and they're not as important. But this is, I think, becomes interesting. So the heap file implementation, and because we say a file could be, or our table could be just a set of pages. So now the question is, if I were to just scan all my data, I mean, I don't know what my reads are. I just want to scan all my data. I can start from a header page. And in this header page, I could store some information. For example, I could say how many full pages I have, how many empty pages I have, or maybe what's the percentage of the empty space in every page. I could store all kind of information, bookkeeping information that I think might be useful for me. As you kind of build a database, start implementing a database, you realize, oh, if I have that additional piece of information, it may help me. And that often something can go to this header page. So it's a bookkeeping and accounting method to kind of keep track of everything. Itself, a header page is a page. So that page, again, can be written to disk. And that page can be brought into memory as well, too. Everything we talk about at the end of the day is a page, and a page is nothing but an array. So for the first assignment, we have the abstraction of just everything is just these arrays. And in the second assignment, we'll push these arrays into pages on disk, and then we bring them into the buffer pool. And so that would be the key addition on the second milestone. But from my header pages, I can just traverse to all the data pages that are full, just the linked list of pages that are full. And I could also have maybe another linked list of the pages that have some empty space in there. So if I wanted to kind of look for a particular record, I could just start scanning all these data pages and see what range of rids exists in this data page. And if my rid is within this, maybe that's the page that I need to be, then that's the page I need to actually examine its contents. If I'm searching by a rid, or if I'm searching by key, for example, I'm searching for John, then, well, I need to just start from this data page, look for anything that has John, any record that has John in it, then I go to the next one, and then go to the next one, and till eventually I find it. Maybe if there's and if John is supposed to be a unique, as soon as I find it, I can stop. Otherwise, I keep continuing. And maybe I go through all these pages, I don't find John, then I go to the other pages. These pages also have some content, but also have some free space. So I still have to kind of search them. But if I'm adding something, then I'm not gonna go to my full pages because I know they're already full. So I'm gonna go to my data to these pages that have some empty spot. And then I'll put it in. And eventually this pages becomes full, and then I add it to the top linked list. So a way to simply just have all my pages linked, and also have my pages indicate which one has free space, so I can quickly traverse to a page that has empty space. So that's kind of a way of thinking about how I have my file, my table is already, I know, span of a set of pages. And this allows me to keep a directory. Essentially, I'm maintaining a directory of all the pages that I have. And all I need to remember is the initial, the head of that directory. And the rest I can, from there, I can discover where they are. So that's the idea. So I have my table with a set of pages. Somehow I need to know how many pages are there, where they are, so I could store that information into a directory. And that's one way of implementing that directory. The other way of implementing a directory, again, I have all my pages. And then in my header page, I could say, well, the first page, I could, for example, have what is the starting grid for this page and how much empty space this page has, or any other metadata that I would like to maintain about this page. I could put it to this slot. And then the next slot in this header talks about the second page. I could, for example, maybe the starting grid of this page, or the end grid of this page, or the free space, or any other metadata. And I can just fill these directory. These are small slots, so a single header page will span many data pages. But then eventually everything is going to be a page, because the concept of the page, it allows me to nicely persist data to disk, push the data to disk, and it nicely allows me to read the data from disk. So eventually this first header page gets filled because I have a lot of more pages. Right now, in each header page, I'm maintaining information, let's say about 16, or I'm maintaining information about 12 pages. So if I have more than 12 pages in my data, then I need another header page. And so I can bookkeeping for another 12 pages. And in the next one, another 12 pages. And now my header pages could potentially be now linked with one another. So that's essentially, I'm kind of building a hierarchy, sort of like almost an index structure over my data pages. It's not a very fancy thing. It's just essentially I'm adding one level of hierarchy to my base data pages. In the previous approach, I was using just connecting my pages with a linked list. So this is a lot more efficient, because in this one, if I need to go to like a 10th page and I don't know what the reference for that is, I potentially have to like do all these linked list hopping. And so there's a lot of random accesses potentially that I need to, from this page, go to the next one, go to the next one. And each of these could be a read, could be a cache miss on my buffer pool. So it's going to cost a lot. In this format, I can just read a single header page, and now I know information about 12 different pages. And in reality, probably a single 4K page going to have information about a lot more data pages. So now the information of the header are really condensed and compressed in a set of small directory. And this is probably a very frequently accessed. So I would suspect that this I can always fit in my memory. So this is always going to be in buffer pool. So it's a very frequently accessed pages. So I'm not going to even flush it out. So I always maintain it in the buffer pool. So then again, that will really simplify the access to these data pages very quickly for me. Instead of this data directory, I could have an index structure. So I could have a B trees, or I could have another index structure that allows me to find the pages that I'm looking for. And I could kind of, again, I can index these pages by saying, what is the starting grid? This is maintains grid from 1 to 10. This is maintains grid 11 to 20. This is maintains grid 70 to 90, for example. And so if I'm looking for a RID of 5 from my index structure, I know this is the one. If I'm looking for another RID, then I know exactly where the physical location of that page is. It could also be the case that the RID itself, that page ID, is not a logical pointer. It's a physical pointer, meaning from that physical pointer, I know exactly the location of that on the device, on the physical device. If it's a physical pointer to the physical device, then I can just do a direct lookup. But oftentimes might be that that's a logical pointer. So I still, from that page ID, I need a physical reference to where that page physically is located on the device. But if I have a very simple design that my table consists of one file, for example, and my page ID 20th would be the 20th page in the file, so then I could just compute the offset of the 20 and construct a physical reference as opposed to my page ID in my RID. So the page ID in the RID could either be a logical reference to the page or it could be a physical reference. If it's a logical reference, we need what? Another level of indirection to translate that logical to the physical address. But if it actually maintains a physical address, then given a RID, I don't need to even to go to the directory. I could potentially just jump into the page. But usually having the directory is it simplifies things. For example, if you have, for example, it could also have just information about the page, how much empty data I have on that page. So as opposed to go to that page, fetch that page, look inside that page, look inside the header of the page, for example, figure out how many empty spots I have, I could just read that from directory. And that will have memory benefits. So again, or less disk accesses, because I can probably cache all my header pages, directory pages in buffer pool, versus I won't be able to cache all the pages that I'm going to just examine for this makes a free space component in my buffer pool. I probably have to pay a cost to bringing it to buffer pool. So again, that's another important benefits of having a page directory. And traditional, most databases, any real database will have a page directory. Any question?
Professor, there's one question on the chat.
So again, that's what we talked about. So it's a page ID, and the offset would be the slot ID. So it could be the slot ID in that page, or it could be the physical offset. So that's both of those are possible choices. The page could be a logical reference or a physical reference. The offset could be a physical or a logical. If it's a physical, it's the actual offset that's in the page. If it's logical, then I need to go to that to the directory inside the page to translate it to the actual physical location. And so again, ask your question. I think it's better to typing it, because I normally don't check the chats. Okay, any other question? Spoken question, not a written one. Okay. So we also have like a system catalog. Again, other bookkeeping, it happens in the database. So let me kind of, I guess, show you the example. That's probably easier. So this is this is not something you have to do, but a typical database will have this. For example, they would have, so it says I have a table called attribute, or I have a table called student, have a table called faculty. What are the field names in that table? For the student, I have a student ID, have name, I have login, age, GPA. What are the types of them? What is the position of that record? What is the position of that field in that record. So these are the information that the database needs to maintain. What is the schema? What are the tables? What are the, for example, even the page directory? All this information needs to be stored somewhere. And at least for the schema information, and also for the indexes, what indexes we have, what are the indexes defined on, what are the different view definition we have, what are the store procedure we have, all of this information needs to be stored somewhere. And well, we store it as tables itself. And well, we call these a special table called the catalog table. And that's, so if you look at a database, you have your schema, you have the table, your user-defined table, but then there's also this catalog table that essentially a way of maintaining the information about the user-defined indexes and tables and so forth. So that's something that, so now why are we talking about this? Well, we also need to do bookkeeping eventually. I mean, you don't necessarily have to have a catalog table, but you could have two tables and you could have indexes defined on these tables. Somehow you need to think about, where am I going to remember this information? I mean, for the first milestone, we're not going to persist anything. So we don't really have to remember anything, but you may still have some in-memory bookkeeping data structure to kind of keep track of some of this information. And that's why the catalog is a very structured way of doing it. And so that's sort of a standard way that it is implemented in databases. So I think that's a good point to switch over. I think the rest are just a summary. And so now getting into the outstore. So if there's no question, then I'll switch to the second part of the lecture.